So welcome back to the last day of this excellent conference. Quick notice from Cheryl. Can you please remember to recycle your badges at the end of the conference, please?
There's a box on the table right near the reception desk. Please recycle your badges. Thank you all for coming. I think it seems like it's been a very productive, interesting week. So we hope to have you back again perhaps in a couple of years.
Well, I think it's happy to say thank you very much for all your work in organising the conference. Thank you. Thank all the other organisers as well, maybe at the end of the day. Great. Well, so, pleasure to see you all. Let's get going. Our first talk this morning is from Michel Rioto, who will talk about inertial and gravito-inertial modes in a spherical shell. Thank you.
Oh, thank you. I would like first to thank the organizers for the invitation, and it's a real pleasure to be back here in Boulder. So I will present you a work that spanned almost 20 years, and present you the last result we have obtained on this, as you will see, a thorny problem. So I will first give some introduction and some words for why we are motivated by this. I just want to recall that in astrophysics and in planets and stars, we are often dominated by rotation. This relative velocity is often quite small compared to the bulk rigid rotation. And so this is because, of course, the size of the objects is very large, and so it's not difficult for the solid body rotation to dominate over the local perturbations. And therefore, this is translated in a non-dimensional number that the Rossby number is always small compared to unity. So if we put this, if we give some numbers just on the Earth, well, we have all in mind the flows in the ocean, where the Rossby number is of order 10 to minus 3, in the atmosphere also, 10 to minus 1, the liquid iron core, where it is very small, but also in young stars, which are rotating fast. Typically, a typical number is 10 to minus 2. And of course, there are also experimental devices that are used. And so just the conclusion is that in astrophysics, the rotation is really ubiquitous and often dominates over the flows. So one problem that, for instance, is rotation is very important, and especially the oscillations of the rotating fluid are the hot Jupiters, which are planets in strong tidal interaction with the star, and for which the dissipation driven by the tides can be quite important. And of course, this drives the evolutions of the system. And this is why we would like to understand very well the way these low-frequency modes are acting on the dynamics of the system. So it's a strong potential way of dissipate energy, and I would like to show you this results, which was obtained by Witte and Savanay now almost 20 years ago, where they computed the torques and the energy dissipation in such a system. Well, it was actually two interacting stars. And what you see here is the evolution of the eccentricity of the orbit. And you see that because of some resonant effect, in fact, what they call the resonant locking, in fact, two modes which are resonating in the star, one which is tending to accelerate the spin of the stars, and the other one which is braking, makes, in fact, the system resonating during some time, and then the dissipation is quite important, and you quite rapidly reach the circular orbit. So that's a motivation for understanding very well these modes in these stars. In fact, when these calculations were completed, in fact, the models are really much simplified. Another important driver for understanding these modes is, of course, the asteroseismology and the understanding of these oscillations of stars, and especially the spectrum of these oscillations. There are many, many stars which are rotating fast and for which we are absolutely unable to invert this spectra. I mean, getting the physics of the stars from this frequency and from the amplitudes, just because the star is rotating too fast. In fact, it's working well when we have slow rotators, because then the theory is simple, but when the stars are rotating faster, then the identification of mode is really complicated. And at the moment, this business is really in its infancy. So these are the motivation. And an additional one is that in the last 10 years, we have a lot of data from interferometry, where we have now new constraint on the fundamental parameters of rotating stars, namely the diameters, the surface temperature. So we have very precise, rather very precise data on the geometric and the mass of the stars, and combining them with the seismological data, that we can hope to have a very interesting physical information on these stars. So let's go back to fluid mechanics, and the first modes which are driven by rotation and by the Coriolis force are these inertial modes. And so I will focus only on an incompressible setup, which is the most simple one. So there are two numbers which are important, the Rossby number and the Ekman number. So we will take the limit of vanishing Rossby numbers so that the equations are linear, and that's a feature of rotating fluids, to be governed by linear equation. It's not because it is linear that it is simple, as you will see. So we focus on this, and especially on the periodic motion of that rise on these rotating fluids. So we have to solve these equations for the velocity field, but if you eliminate the velocity as a function of the pressure, then you get this famous equation, which is Poincaré equation, and which has this peculiarity of being a hyperbolic equation, because the inertial frequency and the inertial modes have frequencies which are all less than 2 omega, and therefore this factor here is always positive, so we have in the end an ill-posed problem, because to this hyperbolic equation we have to match boundary conditions, and you know that any hyperbolic problem, you have to give the initial conditions, and of course if you give some final conditions, then these final conditions may not be compatible with the initial conditions. And that's the sorts of all the problems and the singularities that I will show you. And for that, I mean, I think the easiest way is to have a look to the propagation of characteristic lines, which are associated with the hyperbolic nature of the operator. So in the case of the Poincaré equation, these characteristic lines are straight lines, and well, they represent physically the propagation of the energy of the perturbations. And what you see that in a spherical shell, these characteristic lines are focusing around a periodic trajectory in the meridional plane of this spherical shell, showing up an attractor of characteristics. And along this line, you can just imagine that if you have a perturbation that propagates, when it reaches the attractor, its amplitude, in fact, is growing up to infinity. In fact, in reality, it's not going to infinity because you have some dissipation some viscosity. And, but in the end, you find that the eigenmodes are shear layers that are focused around these periodic orbits of the attractors. And the thickness of these shear layers is governed by the viscosity or the dissipative mechanism that are present. So we have studied these shear layers, and in the case of a 2D setup, that is when you neglect the curvature term of the spherical geometry, which means that, in fact, you consider a section of a torus far from the rotation axis, then you can solve analytically for these shear layers, because the problem simplifies in the sense that there is just a single scale which appears, which is given by the 1/4 power of the Ekman number. And so when you manipulate this, you find that the shear layers, in fact, the cross-section of the shear layer is described by a sort of Schrödinger equation, which describe a quantum particle in a parabolic way as well. And so you can find out all the eigenvalues which are associated with a given attractor in this case. And we have published this in a paper in 2002. In the 3D case, which is the one we are interested in, it's much more complicated, in fact. It's quite surprisingly, we discovered that there are there are at least 3 sorts of modes. So the one which I have shown, these attractor modes around the periodic orbit of the characteristics. But you have also, we discovered recently that there are also critical latitude modes which are associated with a singularity where at the critical latitude, that is where the characteristics are tangential to the inner core. And there are also a quasi-regular mode, and I will focus on these 2 kinds of modes, I mean, because of lack of time, otherwise it would take too much time. So for that, we have to realize that if the frequency of the mode is in fact the sign of some rational fraction of pi, then you can have periodic orbits if the core of the spherical shell is sufficiently small. So in this case, for instance, if the core is 20% of the whole setup, then you have, for instance, this case, you have periodic orbits of characteristics, and any characteristics which starts in the white part remains in the white part, or any characteristics starting in the shadow of the core remains in the shadow of the core. And this has quite important consequences on the spectrum of the inertial modes of the shell. And I show here the case of the main periodic orbits which are associated with the sign of pi/4, which exist whatever the size of the core, because for the other rational fraction it depends on the size of the core. You see that around this frequency, so the square root of 2/2, you have a distribution of the eigenvalue which is very regular. It means that there is a quantization which is just like the one we would expect if the problem was non-singular, was regular. However, this nice picture is destroyed as the viscosity decreases, as the Ekman number decreases. In fact, the perturbations come from the outer parts of this region, and you keep the regularity if you get closer to this frequency, sine over pi/4. And you see that it's just like a wave which pave rather smoothly the spherical shell. Just to show you how it works, We have computed the distribution of the eigenvalues for here a big core, and around this, this frequency. And you see there is nothing, a distribution which looks like random. But if the core is sufficiently small so that there are periodic orbits, you see that the eigenvalues are getting structured and showing up families of and quantization, just as in the preceding case. If I come back to the modes which are associated with attractors, with periodic orbits of characteristics. So in the 3D case, in fact, the structure of these shear layers is much more complicated than in the case of in the 2D case. In fact, what we have discovered is that there are at least 3 scales which are controlling these shear layers. The smallest scale is the 1/3 power of the Ekman number, and which gives, in fact, the wave frequency of the shear layer. The 1/4 power is giving the envelope of the wave packet, and the 1/6 power is giving the position of this wave packet with respect to the local attractor associated with the mode. In fact, we could find a sort of analytical expression of this quantization, but we could not, at the moment, derive these numbers, tau1 and tau2 here, which control the shape of the spectrum in the complex plane. And the consequence of that, analyzing, in fact, the equation, so the Poincaré equation, when it is supplemented by viscosity, gives this 6th-order differential equation. We try to reduce this problem to a simpler one, and in fact, what we found was that, in fact, these 3 scales appear quite naturally, but that means that in this problem, the natural small parameter of the problem is the 1/12 power of the Ekman number. So if you realize that the smallest Ekman numbers are in stars, yes, it's about 10 to minus 18, and that's using the molecular viscosity and the size of the star. Well, you see that even for these very small Ekman numbers, this parameter will not be very small. And so actually, deriving the asymptotic theory for these modes is interesting, I mean, for the sake of mathematics, and maybe for some results which would work for the numbers which are of order 10 to minus 12, for instance. So that's what I wanted to say about inertial modes, pure inertial modes, and now I will talk of some generalizations of these modes when we add some more physics, as we have in stars or in planets. So the first thing that we investigated was the addition of stable stratification, so that in this case you combine gravity modes and inertial modes to have these gravito-inertial modes. And what it changes is that, in fact, the Poincaré equation is transformed into a mixed type equation. So you have region of the shell where the equation is elliptic and other regions where it is hyperbolic. And I show here some result that Boris Dintrans obtained during his PhD thesis. So you see now that for instance, this attractor mode has characteristics which are curved and that bounce on for instance, on the turning surfaces which separate the elliptic regions and the hyperbolic region. And we have also new kinds of attractors, which are those made by the wedge when the turning surface meet the boundary. And here you see that the characteristics are focused in this wedge, and so they generate new kinds of singular modes. However, if you have a differential rotation, which is also the case in stars, and I show here a model of 5 solar mass star, which rotates at 80% of the critical angular velocity. This is the angular velocity of the star, and you see that the core is rotating faster than the envelope. The equator is rotating slightly faster than the poles, so you have differential rotation everywhere, actually, in the envelope. And so we have investigated the case of these inertial modes in the case where you have some gradient of the angular velocity. And what we found was that also in this case, the pressure perturbation equation is of mixed type because these quantities depend on the location. And so they are related, in fact, to the distribution of the angular momentum. And again, you can have periodic orbits of attractors, so the focusing of characteristics. But here you see that you just need the bouncing on this turning surface. The core doesn't play really any role. And you have also singular modes. You have also for non-axisymmetric modes a role played by the critical layers, where the wave, the phase velocity of the wave reaches the velocity of the fluid. You might have also unstable modes, just because you can transfer energy from the differential rotation to the modes. So it depends also on the way on the differential rotation that you consider. In fact, we have in this work we have considered only the what's going on? Oh shit. Well.
Do you have it here too? Put it on the drive?
No, well, that's.
It's his laptop.
Oh, it's my laptop, yeah.
It's coming back
crazy.
up, though.
Yeah, maybe it will come back.
Just
yes.
Just hopefully it won't
Crazy
any
window. In this case, no. It was pure differential rotation in an incompressible fluid. I will show the combination of the two. That was the next step. Okay. So. Great. Where am I? So I have to unplug. I'm here. Okay. Okay. Yeah. Okay. So 10 seconds. Okay. So I was here. And yes, so the last work we did on this subject was combining stable stratification and differential rotation. And in fact, using the fact that in a rotating frame, if you have a stable stratification, then you have a baroclinic flow. So we could derive the differential rotation from the stable stratification. And in this case, as you can imagine, the solutions are rather complex. In fact, you have a lot of cases. This is the frequency of the mode as a function, and here this is the Brent-Vesely frequency, and the different region of this plane just mark the different possibilities that you have. And I think it will be clear with that in all these cases, for instance, you have, in black, you have the elliptic region, and in white, the hyperbolic region. And so according to the frequency and the amplitude, the intensity of the stratification, then you have these different possibilities, or the propagating cavity, the shape of the propagating cavity. I show here an example of these, of one non-axisymmetric mode, which I think is unstable because, well, there is here this co-rotating layer. So I come to the conclusion. In fact, what I would like, one of the messages is that you can take with you is that the rotation makes the dynamics quite complicated. I mean, it's just the Coriolis force. Even if the things are linear, there is a lot of cases. Many scales, in fact, pop up in this problem. And what we have identified is that, well, when you have differential rotation, you can have instabilities of some large-scale modes. And the open questions are that, for instance, are these large-scale modes observable in stars? And do they participate to the excited modes that we see in asteroseismology? What we would like to have is an asymptotic theory of these inertial modes. We have not managed yet to get this asymptotic theory, probably because we just realized that the 1/12 power was the small parameter, and we have to redo the machinery to get these expansions. And of course, for stars, we wonder about the role of the compressibility and the fact that the density is very much varying along the radius. And we have done some computation in this case, and I will end this talk with this nice picture of a gravito-inertial mode in a centrifugally distorted star, where you see that the distribution of the kinetic energy of the mode is quite complicated. And if we detect such modes, then we will have some information on the interior of the star, but on specific regions. So we have to detect many of such modes to reconstruct the distribution of the sound velocity, the stratification, and the rotation rate in the stars. So I will stop here. Thank you for your attention.
Very much for a nice talk. Questions?
Well, that's a great talk. Do you think that differential rotation can drive the Rossby waves that have been observed in the sun?
I don't know, actually. The Rossby waves that have been observed are non-axisymmetric inertial modes. Can they pipe energy from the differential rotation? I don't know. To be honest, I don't know.
Questions? Yes, go ahead. Probably simplest.
In my case, actually, I hate inertial modes because I do dynamo simulations. And if you lower the command number, they start to come up all the time. Is there an effective way of suppressing those modes, or you just have to crank up the like the inertia term in your Coriolis for just increase the Rayleigh number or something like that.
Yeah, it's true that they are very demanding on the spatial resolution. I mean, to get these results, we had to push the number of spherical harmonics to describe these modes to the highest values. I mean, some of the lowest Ekman numbers that we have, with which we have computed this mode, 10 to minus 12, required about 4,000 spherical harmonics. So we pushed the machine to the end. And yes, Frank.
Concerning your last picture, in our precession experiment, the little water experiment, we have a very strong driving, and we get an deformation of the former solid body profile. And by looking for a sort of spectroscopy of inertial waves by changing the frequencies of the M5, M6 modes, we can really do a sort of inverse problem by inferring on the V phi of R by the changed velocity. This means you can do indeed something like a spectroscopy based on inertial waves. So I think it's quite promising.
Yes, I think the information that you can extract from the detection of inertial waves is the rotation rate at different depth, for instance, in the star or in the planet.
Let's thank Michel again. Thank you, Michel.
Thank you.
All right, so our next speaker is going to be Adam Showman from the University of Arizona. And he's going to talk, unless he changed the title in the end, about atmospheric dynamics of giant planets and brown dwarfs.
Advanced slides. Hello. Okay, today I'm going to tell you about the atmospheric circulation of the giant planets and also brown dwarfs. We've heard a bit about Jupiter so far, and I'll touch back on some of the results we've already heard in this talk. But we haven't heard much about brown dwarfs yet. I'd like to convince you that these are interesting astrophysical objects of relevance to GFD. Let me start first with a brief summary of the observations that we're going to try to understand of Jupiter and Saturn, and then describe a bit about brown dwarfs before discussing some of the specific theoretical and modeling issues. So this shows visible wavelength images of the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, shown to scale. And the zonal mean zonal winds are shown here on in the bottom row here with scales that are different in each case. And as we've seen before, we've seen this in detail for Jupiter, of course, has alternating east-west zonal jets. Saturn as well. The speeds are a bit faster on Saturn than Jupiter. These are sister planets in some way. They're loosely speaking qualitatively similar. They both have eastward or super-rotating jets at the equator. Uranus and Neptune are a bit different. They're smaller, of course. They seem to have a jet pattern that's closer to a 3-jet structure with high-latitude prograde jets and then sort of low-latitude retrograde or westward flow, and with a bit more scatter associated with waves and so on. The clouds that we're seeing here are, roughly speaking, at a pressure of about 1 bar, and these winds are obtained by tracking small cloud features over periods of a few hours. So these represent the winds at about the 1 bar pressure level. And as Yohai described, Juno has provided constraints for Jupiter and Cassini for Saturn on what the wind structure is doing below that level. And so for Jupiter, we know the winds are penetrating several thousand kilometers of order below the clouds, and for Saturn as well, at least for the equatorial jet, penetration of quite a few thousand kilometers is required. Uranus and Neptune, however, the winds, relatively speaking, seem to be shallower, confined to, at most, the outermost 0.2% of the mass, also a result that Yohai and I worked on associated from the gravity results. What's happening above the clouds? So above the clouds, we have a stratosphere, and there are no features that we can track, but there are thermal structures, and this gives a sense for Jupiter of temperature versus latitude in a zonal mean, showing time over several decades. And the variations are just a few Kelvin as a function of latitude, and they're correlated with the banded structure that I showed you earlier in such a way that in most cases there's a thermal wind pattern where the jets are getting weaker as you go up into the stratosphere. And interestingly, there's this low latitude oscillation. You can see this variation over time, which turns out to have a period close to 4 years and has been dubbed the quasi-quadrennial oscillation. And it seems to have a behavior somewhat similar to the behavior of the quasi-biennial oscillation in the case of the Earth. Before I mention that in more detail, let's look at Saturn. Saturn also, it turns out, has a similar oscillation where the observed temperatures in the stratosphere vary over time, with most of the variation that we're talking about here happening near the equator, low latitudes, within 30 degrees or so. And these are all rapidly rotating planets with rotation periods of sort of 10 to 11 hours in the case of Jupiter and Saturn. So the Rossby numbers are very small. Thermal wind balance holds, and so that one can, from the temperature structure, infer something about the zonal winds. One has to do a bit of extrapolation across the equator, but we seem to have a basic understanding of what's happening. And this shows the structure of the zonal wind anomaly that is obtained by these observations. So red is showing eastward, blue is westward, the x-axis is latitude, the y-axis is pressure, showing several scale heights here. And so you can see this alternating pattern of stacked westward and eastward jets centered near the equator. This is in 2005 and 6 from Cassini observations. And then about 5 years later, we can see a similar structure, but the whole structure is shifted downward. This eastward peak is shifted downward by nearly 2 scale heights. This shows some thermal data illustrating that the oscillation has a 15-year period, which is almost exactly 1/2 of a Saturn year. So this has been dubbed the Saturn semi-annual oscillation. And it could be that the fact that it's roughly half a Saturn year is relevant, that there's a locking going on there. So this seems very similar to the case of the Earth. This shows the quasi-biennial oscillation. This is showing the zonal wind, showing westerly and easterly patterns as a function of time with a period that's a bit more on average than 2 years. And so if you were to look at any given altitude, let's say 30 kilometers, then, and this is at the equator, so at any given altitude, let's say 30 kilometers, then at the equator, the direction of the equatorial jet is oscillating in time from westward to eastward and back and forth. And so this phenomenon in the Earth case has been very well studied. The mechanism was first worked out in broad form by Lindzen and Holton in the 1960s and 70s. Daniel gave a very nice talk on this on Monday, and there were some experiments by Alan Plum even in the 70s, and a whole sort of suite of theoretical and modeling results. This phenomenon was only captured in full 3-dimensional circulation models starting in the late 1990s. As I'll describe in more detail later, it's driven by a wave mean flow interaction that requires rather high vertical resolution to resolve. And so that was only sort of acquired in GCMs starting in the late 90s. Even to now, though, this phenomenon in GCMs is often only associated with, or at least accurately simulated, if you put in parameterizations for the drag or accelerations associated with waves that are not actually being resolved in the model. And for the Jupiter and Saturn case, the situation is sort of much less further along. There's only been a couple studies looking at this phenomenon theoretically for the giant planet case. Okay, let me turn briefly and tell you about brown dwarfs. So brown dwarfs are objects intermediate between planets and stars. There are different definitions. Let me not talk so much about origins. I mean, they're often thought to form like stars rather than the way we think Jupiter formed. One could perhaps define them as having masses of sort of 10 to about 80 Jupiter masses. Because they're more massive than Jupiter, they cool off rather slowly. There are, of course, some orbiting stars, but most of the ones that we're observing and getting good data on are field objects. They're isolated, and so there's no star nearby, which makes them easy to get to observe. We have good infrared spectra. So they cool off over time, but if there are 40 or 50 Jupiter masses, then even after many billions of years, the surface temperature, meaning the temperature of the photosphere, basically, can still be 1,000 Kelvin or more. And these objects have, of course, a continuum of masses from 80 Jupiter masses down to Jupiter, and therefore also a continuum of temperatures. And of course, these have been sort of classified. It's not working too well. So we have from M to L to T, and then this is actually Jupiter itself, and these spectral classes. I won't go into the details, but just as for stars, there are different sort of changes in the spectral signature that define these different classes, but basically they signify sort of a decrease in temperature of the object. So for example, for M and L, one sees a few bumps and wiggles, but loosely speaking, kind of a broad Planck type function here. So, where you're basically, and this is radiation coming from a layer where the temperature is varying greatly with altitude. You're basically seeing the top of the convection zone. And so if you see something that's close to an adiabat, that's close to a sort of a black body, loosely speaking, then that suggests that there's something blocking the absorption bands. So one can only explain these kind of data with a global cloud deck. On the other hand, the T-dwarfs, you see these enormous spectral bands of methane and water and so on. And it seems that the clouds have effectively sunk below the cloud, below the visible photosphere. So that the observable part of the atmosphere is closer to being cloud-free. So we have observed such objects all the way from temperatures greatly exceeding 1,000 Kelvin down to 250 Kelvin or so. And there's even a class of planets that are being discovered around other stars that are directly imaged. So this shows the most canonical example, HR 8799, 4 planets that are observed orbiting a star with masses that are a few Jupiter masses, maybe 5 Jupiter masses. They are tens of astronomical units from their star. There are lots of questions about how they formed and so on. Thinking just about the meteorology, they're basically like brown dwarfs. They're just sort of low gravity, low mass versions of brown dwarfs. They're so far from their stars that the irradiation from their stars is irrelevant. They have temperatures of order 1,000 Kelvin. And also through Doppler, as with brown dwarfs, we know that they're very rapidly rotating. So just to describe briefly some of the observations that we have indicating atmospheric dynamics. So I alluded to the existence of clouds. So of course, the sheer existence of clouds, let's not forget, requires some sort of dynamical mixing to loft the particles, the cloud particles. There's also disequilibrium chemistry. This thing's not working. Let me switch to the other one. So there's, one can have methane and CO, and it turns out that there's quenching between these, where in many cases the observed value, the observed ratio of these is different than an equilibrium. The equilibrium ratio is a function of pressure and temperature. So for example, on Jupiter, there should be no CO at all. And in fact, 1 part per million of the carbon is in CO, which doesn't sound like a lot, but that's like 10 orders of magnitude more than it should be. However, down deep at sort of hundreds of bars pressure, most of the carbon should be in the form of CO. So the standard sort of explanation for this observation is that there's dynamical mixing where air with lots of CO is brought up from depth, and it gets quenched where the dynamical mixing time is fast enough that you can't revert back to the, it can't cause the carbon to revert back into the form of methane. And so from these observations, one can actually place some constraints on the vertical mixing rate. Perhaps more excitingly, in the last 10 or so years, there's been observations of variability, light curve variability in the infrared for a wide range of brown dwarfs. So you can imagine a brown dwarf that might have patchy cloud structure, and as the brown dwarf rotates, cloudy and cloud-free patches rotate in and out of view, and the tops of the clouds are relatively cool, and let's say J-band or some near-infrared wavelength, a couple microns, let's say. And so the tops of the clouds don't radiate much. The holes in the clouds are seeing deeper, where it's much hotter. They radiate a lot. And so in the infrared, you see this very patchy structure. And so as the brown dwarf rotates, the global integrated flux goes up and down. And so that's shown in this sort of slide here. And so the total flux here is varying by about 5%. The x-axis is time, and this is showing a period of 2.4 hours. So this brown dwarf has a rotation period of 2.4 hours. And these are observations taken from a ground-based telescope over a period of several days. So coming back a few days later, you can still see the thing varying with a few percent amplitude. The period is exactly the same, but the shape of the light curve is different. So the period has to be the same. Of course, you can't change the rotation period. But if you alter the pattern of the patchiness on the surface, then the shape of the light curve will change. For instance, from something that's quasi-sinusoidal here to something with a kind of a peak structure there. So that indicates evidence for atmospheric dynamics, that on timescales of a few rotation periods, the pattern of the patchiness on the surface is changing. And then there's even been a couple brown dwarfs where the Doppler imaging technique has been used, a technique that's been used for a long time to image rapidly rotating stars using the time variation of the Doppler shift of individual spectral lines. And one can use that for brown dwarfs to obtain an image of the patchiness that exists on the surface of brown dwarfs. So this is sort of subfield is just beginning now. In any case, so all of this indicates an important role for atmospheric dynamics. Let me describe briefly the dynamical regime of brown dwarfs. So they're rapidly rotating. We know from, if you imagine Jupiter rotates with a 10-hour period, so the inertial space velocity at the equator is 12 kilometers a second. So that's pretty good broadening of a spectral line. If you imagine that translated into a Doppler shift. A brown dwarf that's rotating with a 2-hour period, let's say, you're talking sort of 50 kilometers. So that's pretty easy to measure. So just from measuring the so-called V sin I of the individual spectral lines, the broadening, we can actually obtain a measure of the rotation rate, which can then, of course, be confirmed for brown dwarfs where we actually directly measure the variability. So this indicates typical periods of kind of 2 to 12 hours, and for any reasonable wind speed and global sort of large-scale length scales implies rotational domination of the flow. Rossby number is much less than 1. We expect, of course, the interior to be convecting, and then it has a stably stratified atmosphere overlying it. Different than solar system objects, though, or most exoplanets, there's no external radiation. The primary mechanism for driving the atmospheric circulation on the Earth, or on a hot Jupiter, let's say, is the strong starlight and the gradient of the stellar heating. So in the Earth case, between the equator and the pole, or for a tidally locked planet like a hot Jupiter, between the day side and the night side. And so that drives everything as far as at least the large-scale circulation on the Earth, let's say. However, lacking a nearby star, these objects lack this mechanism. And so if you ignored anything that was happening down in the convection zone and just imagine the stratified part of the atmosphere, you might wonder whether it would just go into a state where the stratified atmosphere is being bathed in radiation coming up from below. The convection zone, to zeroth order, is going to have the same entropy everywhere. And so to zeroth order, that flux coming out should be the same at the equator and the pole, and ought to lead to a radiative equilibrium temperature structure in the atmosphere that's independent of latitude. Very different than the Earth case or the hot Jupiter case. However, one is going to have convection in the interior, and so that convection will most likely trigger waves in the atmosphere. This is an example from Freytag et al. From 2010, where they do a small two-dimensional box simulation, neglecting rotation, with a domain of about 500 or so kilometers on a side, so a very tiny fraction of a brown dwarf. And this illustrates the convection. This plot is showing entropy perturbations. And so you can see the convective structure here, and it triggers a wide population of gravity waves. And so it turns out that for the case of, say, Earth or Jupiter, that the generation of these wave types in the troposphere and their propagation into the stratosphere is one of the main ways of driving the stratospheric circulation. And so we suggest that this same mechanism should be relevant to, to brown dwarfs as well. Before I get into that in more detail, to just summarize in kind of review talk style, a few of the questions of interest that we might like to address. What's the nature of the circulation? And these kinds of questions are relevant to the whole body of brown dwarfs as well as Jupiter and Saturn. To what extent, just theoretically speaking, should we expect that the circulation should comprise zonal jets versus vortices, storms, turbulence? What controls the amount of energy in these, their interactions? What are the characteristic wind speeds and horizontal temperature variations, the energy-containing length scales, the time variability? How does all of this scale with parameters like the internal heat flux, the amount of starlight received, and so on? How does the circulation work? What are the actual dynamical mechanisms controlling it? What is the role of condensation in clouds? This is likely important for Jupiter and Saturn, and even more so for brown dwarfs, where radiative feedbacks are likely to be critical. And there's this sort of broad question we could wonder, is it possible to achieve a unified theory of giant planet atmospheric circulation that can span the range from kind of Jupiter and Saturn on the one hand to the hottest of the brown dwarfs on the other hand? And of course, there's a lot of interest in the exoplanet field and smaller planets, and all the way going down to terrestrial planets that might potentially be habitable. But these largest of the planets are by far the most observable. And so if we can work out theories for those planets that have relevance, perhaps we could then extrapolate those, or at least get insight into how smaller planets might behave, even if we can't observe them as well. And so to aid in this effort, there's actually information booming, observational constraints, let's say, from several different fields for objects with very different parameter values. So hot Jupiters are giant-sized exoplanets that are very close to their stars, maybe 20 times closer than Earth is to the sun. So they receive fluxes of 10 to the 5 or 10 to the 6 watts per square meter. They're very strongly irradiated. Modeling work suggests that their heat flux from the interior is weak, so like that of Jupiter. So the ratio of what they get from their star to what's coming out of the interior might be 10,000 or 100,000. They are probably close enough that they're tidally locked, so they have a permanent day side and a permanent night side. So if the orbital period is typically a few days, that implies a rotation period of a few days. So rotation will be critical. The Rossby number might be of order unity, but not nearly as dominant as it would be for, say, a brown dwarf or the Earth's atmosphere or oceans at large scale. Then, of course, solar system giant planets are weakly irradiated by the sun. They have weak interior fluxes. These are comparable to a factor of a couple. They rapidly rotate. And then brown dwarfs and directly imaged planets barely get any starlight at all. They have a strong interior flux, and they rotate very rapidly. And just to sort of illustrate this a bit better, we could actually put this on a regime diagram where on the x-axis I have the interior heat flux in watts per square meter, and on the y-axis the external flux received from the star in watts per square meter. So this little magenta line is where the two fluxes are equal. So we have the giant planets down here, Jupiter, I've drawn Jupiter and Neptune down here where the fluxes are comparable and very weak. Hot Jupiters are up here with fluxes orders of magnitude larger than our solar system giant planets from the star, but not much coming out internally. Brown dwarfs are the reverse, and these are the different spectral classes which correspond to cooler and cooler brown dwarfs, and there's of course a continuum to Jupiter. We've pretty much observed down to about a few hundred watts per square meter here. And then there's a small population of brown dwarfs that are very close to their stars where they have enormous internal fluxes and enormous fluxes received from their star that are probably comparable. And so if you think about it, we have this enormous parameter space with observations pinning all four corners of it, which might give us some hope of actually tying down theories. If there's some theory we might have for how the wind speeds or the structure of the circulation should scale with either of these heat fluxes, having these observations pinning the endpoints of many orders of magnitude in parameter space, I think will be quite useful. But these are all from different fields, you know, the brown dwarfs and exoplanets, and of course Jupiter. I mean, the people in these different fields publish in different journals, and they go to different conferences and so on. So there's some field hoppings needed to take advantage of this. So let me focus specifically now on trying to describe some numerical simulations that relevant for brown dwarfs and Jupiter and Saturn. There's been a long history of two-dimensional and quasi-two-dimensional turbulence models relevant for Jupiter to describe how we can get zonal banding on the giant planets. So this shows an example from Scott and Pavani from about 10 years ago. This is an example from my own work with a former graduate student, Yuan Lian. And so in these kinds of calculations, for instance, in this case, it's a shallow water model where turbulence is imposed artificially, or in an ad hoc manner, I should say. And then one studies how the jets are generated. And there are actually no models that are sort of relevant for the regime of brown dwarfs yet. And also, there's no three-dimensional models of giant planets that have generated these kind of QQO or Saturn semi-annual oscillation-like phenomena. So a few basic questions. What would be the circulation like in the regime of brown dwarfs, where it's much hotter, therefore the radiative time constant is shorter, so it's a bit different than Jupiter. Fast rotation rate, and what would be the implications for observations. We'd like to understand how interior convection interacts with the stratified atmosphere to see if we can produce jet streams in general, perhaps relevant to Jupiter and Saturn, and also see if we can explain these oscillations in the stratosphere. So I might be short on time, so I have a little theoretical thing that maybe I'll skip, but this is sort of just a schematic showing the kind of wave-driven circulation that I mentioned earlier. So you imagine if you have waves that propagate up, Rossby waves, let's say, that propagate up from below, and if they break or get absorbed in sort of a self-organized manner, then they can potentially drive a zonal flow, and so that is labeled here as the primary wind coming out of the board. And then in a steady state, that would be balanced by the Coriolis force associated with a meridional circulation. So you get the secondary circulation And in the case of a brown dwarf, let's say, this can bring up, or even Jupiter and Saturn, this brings up cold air from below, low entropy air from below, high entropy air is advected down because it's stratified. And so you get this horizontal temperature difference, which is mechanically driven. So of course the hot regions the cold regions are the ascending regions and the hot regions are the descending regions. So it's thermally indirect, it's a mechanically driven circulation, just like we have in the Earth's stratosphere and the stratosphere of Jupiter and Saturn. So one can actually try to do a little order of magnitude theory of this to try to come up with estimates of how what one would actually expect for this horizontal temperature difference and for the wind speeds and so on, which I think I'll skip in the interest of time, because I think I'm going slower than I thought I would. So let me just describe some of these three-dimensional circulation models. This theory that I mentioned predicts for typical conditions, either for Jupiter or going all the way out to brown dwarfs, that you would have wind speeds of order tens to a few hundreds of meters a second, horizontal temperature variations on an isobar of a few to maybe 100 Kelvin or so, depending on parameters. So that's kind of the range, and that's consistent with what we see on Jupiter. If we put in Jupiter values for such a theory, we roughly reproduce Jupiter, and it predicts that brown dwarfs should have maybe perhaps slightly faster wind speeds and bigger temperature differences, but not by a huge factor. So to look at this problem in detail, I've done three-dimensional simulations using the primitive equations, just of the stratified part of the atmosphere and sticking just a little bit down into the convection region. And you could view this calculation as a three-dimensional kind of generalization of this long history of turbulence studies going back to Williams and Scott and Pavani and so on. So I include full vertical structure, but then I perturb it at the bottom in a random, spatially isotropic manner, where the random pattern is varying randomly in time over some characteristic time scale. And then I use Newtonian cooling for radiative damping with some characteristic radiative time scale. So this shows a sense of the thermal structure, where we put the thermal forcing at the bottom. And so this generates a wide population of waves that then interact with themselves and with the mean flow to generate zonal winds and other features. So this shows an example. So this is 4 calculations where all the parameters are the same except for the radiative time constant. And importantly, in this context, radiative time the radiative effects are a damping on the flow because of the fact that there's no external star. And so the radiative temperature profile that the radiation is relaxing to is the same everywhere. So radiation plays the role of removing energy from the flow. The energy is being put into the flow by the convective perturbations at the bottom. So when the radiation timescale is long, the radiative damping is weak and the zonal jets are faster, 400 meters a second in this case. And when the damping is stronger, then the jets are weaker. And you can see that there's a change going all the way, more than an order of magnitude variation in the wind speed. We put in a little drag boundary layer at the bottom, which maybe parameterizes the idea that the jets, as they penetrate into the adiabatic region, ought to follow, loosely speaking, kind of Taylor-Proudman type behavior and perhaps stick down into regions where MHD forces or other damping would be important. And we can vary this parameter as well. When the damping is weak, then one gets very nicely banded zonal jets with a superrotation, as shown here, sort of Jupiter or Saturn-like. When the drag is stronger, then the flow, of course, is more damped. And so the one also gets, this is showing the potential vorticity in a couple different models on the left panels with the relative vorticity here. The top panel is a model that resembles Jupiter and Saturn loosely in a fairly nice manner, where one gets homogenization of the potential vorticity in strips, which says something important about the mechanisms of jet formation. And one gets alternating zonal jet patterns in this particular case with a nice superrotation at the equator. And so this is a more weakly forced model in the top row and a more strongly forced model in the bottom row. And you can see the more turbulent structure in this case. And interestingly, we obtain this oscillation that I alluded to at the beginning. So this is showing up in the stratosphere of this model. The zonal jet structure, east is red is eastward, blue is westward. And so at the equator, this is a single simulation over time, and at the equator, you can see the jet is oscillating in sign between eastward and westward with a time scale, in this case, of about 12 years. So this is the meridional structure of this sort of oscillation in this simulation. So latitude in each panel versus pressure. And this is showing time in Earth days for the simulation. And so you can see red is eastward, blue is westward. So you see this stacked pattern of eastward and westward jets that then sort of migrate downward over time in the way that we observe for these oscillations on the 3 planets. And this shows the zonal mean zonal wind at the equator over time in one of these models. So this is kind of the troposphere down here, and the model stratosphere. And so you can see red again is eastward, blue is westward. And so you can see at any given altitude, the jet at the equator is alternating its sign from east to west on a long time scale. And, but the whole structure is migrating downward, as we see with the QBO and the Saturn and Jupiter oscillations. In this case, the period's rather long. These simulations are fairly demanding computationally, so it's hard. I haven't fully explored the parameter space, but a goal one would want to achieve is to understand in detail what parameter regime, as far as the damping parameters and the forcing parameters and so on, allow such a phenomenon at all, and of course how the properties, such as the period and the amplitude, depend on these. So Daniel described the mechanism quite nicely on Monday, and I don't have much time here, but basically you imagine waves that propagate up from below, and the waves are absorbed by critical levels on the zonal jets in a way that allows the wave forcing and damping to self-organize. And so what tends to happen is that on the bottom flank of say, one of these eastward or prograde jets, that's where you get the critical levels where you get absorption of the eastward propagating waves that then, when they are deposited, cause an eastward acceleration. And likewise, westward propagating waves don't get absorbed there. They get absorbed at the bottom of the westward jet, where when they are absorbed, they produce a westward acceleration. And so the key point is that there's a self-organization of the wave acceleration, where the peak of the eastward acceleration occurs on the bottom flank of the eastward jet, and the peak of the westward acceleration occurs on the bottom flank of the westward jet. And because the peak in the acceleration is shifted downward from the peak in the jet itself, then that causes a time evolution where the whole jet structure moves downward over time. And this is basically from one of Plum's papers in the 70s. So just to conclude, so the giant planets, Jupiter and Saturn, of course, have nice zonal jets, and they have these very interesting stratospheric oscillations analogous to that on Jupiter and on Earth. And I hope I've convinced you that brown dwarfs are interesting astrophysical objects that can complement our understanding of Jupiter and Saturn. The dynamics of these objects are rotationally dominated. I presented three-dimensional calculations that produce banded zonal flows under conditions of weak damping that are, in some cases, very similar to that of Jupiter and Saturn. And this is the first time that these long-period stratospheric equatorial oscillations have been captured in a full three-dimensional model of giant planets. And also, let me just end with the point that these models are, of course, highly idealized and neglect any role for cloud feedbacks. On brown dwarfs especially, this is going to be quite important, most likely. And even for Jupiter and Saturn, we see this banded cloud pattern, and that alters significantly the latitudinal pattern of how the sunlight is absorbed and the exact pressure levels from which infrared radiation to space come out, which almost certainly has a huge effect on forcing the circulation. So that needs to be included in future models. So I'll end there. Thank you.
So at the Cassini Science Symposium last month, it was discussed that Cassini's ultraviolet spectrometer did a series of stellar occultations of the upper Saturn atmosphere during the final mission and got really beautiful data, which seems to indicate our unexpected equator-to-pole temperature structure in the upper atmosphere. And I was wondering if this mechanical forcing of circulation could help explain such a thing.
Do you know what pressure roughly that corresponds to?
I think it was up near mesosphere type altitudes.
Below the thermosphere?
Yeah, below the thermosphere. Yeah.
Okay, well, that could well be relevant. Yeah, Jupiter, well, Saturn, of course, has an obliquity that's slightly bigger than Earth. So there's a very nice seasonal cycle on Saturn. It doesn't get down into the jet structure. So throughout Saturn's 30 Earth year long, year, we don't see very much variation seasonally in the jet structure because at pressures of a bar are deeper, the radio times are much longer than a Saturn year. But there's a huge, you can see very nicely in the data, an enormous equator to pole temperature variation at pressures less than maybe 30 millibars or something associated with the seasonal cycle. And so that probably drives a meridional circulation. And there's coupling to the photochemistry because you get ethane and acetylene produced by photochemistry, both of which are radiatively active and they have different chemical destruction timescales. So it's a very interesting coupled system that actually has not yet been modeled in detail.
Nice talk. I wanted to ask you about the last part of it, which went by pretty quickly, about the forcing to produce the zonal flows. A couple quick questions on that. First of all, in the observations of Jupiter and Saturn, you see that the width of the zones and belt system decreases as you go from the equator to the poles. It's not a bad fit to have 2 pi times the local deformation radius, which is an interesting length scale because it's where kinetic energy goes to potential energy. Do you get that kind of trend in your simulations?
Yeah, I mean, you know, you're saying with the jets being stronger at the, wider at the equator. And
Exactly.
Yeah, I think we do. I
Okay.
mean, you know, I don't think I quantified it in detail, but just let's see to illustrate the. Yeah, I mean, it's perhaps a subtle effect, but you know, one could perhaps argue that these jets are a bit narrower than the ones at the equator.
It'd be interesting to quantify that.
Yeah.
The next question is how does if you plotted that at different radii or elevations of the planet, how much variation do you get in your zonal flows, you know, between, you know, the bottom of the stratosphere and the top of the troposphere? And how would that, you know, fit with a thermal wind interpretation if you use, say, Lee Fletcher's infrared data?
Yeah. Okay. So this structure, so the flow structure down deep is fairly barotropic, which is largely just a function of the fact that, you know, we're transitioning to something. This calculation, the flow transitions to something that's close to an adiabat down deep, such that vertical motion isn't going to induce large horizontal temperature variations. And this structure is fairly stable. Like this equatorial superrotation, for instance, is not flipping in sign. This is a stable structure in this calculation. And then on top of that, you have you know, this oscillation that I mentioned. And so in some of the calculations, if there's no strong superrotation, the jet will just actually oscillate in actual sign from east to west, like the plot that I showed. In this case, it pressures several scale heights above this. There's one of these QBO-type oscillations, but just varying around this, so that sometimes, you know, if you were to plot a height structure, like, you know, you'd see basically, you know, an oscillation in the strength of the superrotation with height, and that that structure migrates downward with time. It's basically a sort of a QBO with an amplitude that's weaker than this jet itself that's stamped on top of the jet.
Right, we have to move on, so let's thank Adam again.
Yeah.
It's my pleasure to introduce Jules Samaria, who will talk about experiments on weak turbulence with surface and internal gravity waves.
No.
Very soon,
It's
very soon.
Not that one. I don't know anything about that one. Should it work? Voila. Okay. So let me start by thanking the organizers for such a nice meeting and for such a great location. And well, it seems like I'm the only one that will talk about anything about geodesy or the Earth's orientation and things of the sort. And so I'll start with an introduction. This is the title of the introduction. And you see, sometimes when I talk to old friends and things like that, they sometimes ask me, "So what do you do?" And I say, "Well, I'm a scientist. I do fluid dynamics of rotation." And then they immediately say, toilets, you know, flushing toilets. And they start telling me, "Oh, you know, in the northern hemisphere they go one way, in the southern hemisphere they go the other way." And then I proceed to tell them, well, it's not the case. That is just an urban legend, that it doesn't happen. And I had many occasions that went like that. But one day, this thing happened again. A friend was telling me this thing about the toilets, and I kept saying that it was not true. And they said, no, but I actually went to the equator, and there is in this place called I think it's the Museum of the Sun in Ecuador, in the country, Ecuador, and they have a monument, and they have the line of the equator painted on the ground, and so they have a demonstration. So they have a basin full of water right at the line of the equator. So there is a person there, like the person showing the experiment, and a lot of tourists go to this place. It's actually packed. And so the demonstrator starts with the basin, and he starts telling the story about the Coriolis forces and the equator and things like that. And then he puts some leaves on top of this basin, and he proceeds to pull the plug under the basin, and the basin drains immediately without rotating. And then immediately after, he moves to the other side of the equator, fills the basin again, right? Puts some leaves, pulls the plug, and right on, keeps going. Immediately after, goes to the other side, and does the same thing and spins the other way. So my friend was telling me the story, and I was like, that's impossible, that cannot happen. Because of, I tried to explain about the Rossby number, the inertial forces, Coriolis forces, and but it happened, sure, it's there. So I looked it up, and I found the video. I'm not going to show you the video because it's a little bit long. But the explanation is that, of course, the demonstrator waits for a long time when the basin is in the center. And of course, there's no motion in the water, mostly. So he pulls the plug, nothing happens. But when he moves to the side and fills it up, he just fills it on one side. So and then does the same thing on the other side. So that's the explanation for why this works. And this is usually a slide that I put for explaining what the Rossby number is. But even, I was thinking about this, even if if you could ignore the inertial forces and if you could just amplify the Coriolis forces, this wouldn't work either. Because the Earth's rotation, the orientation of the rotation, is changing in time quite a bit. For example, this is the trace of the North Pole over maybe 30 years in the XY plane. This is actually arc seconds. But it amounts to about 30 meters at the North Pole, or South Pole, if you want. So, of course, the line of the equator will be shifting accordingly. And so, even if you had ignored the inertial forces, then the line of the equator will be changing month after month, and you wouldn't be able to perform this experiment. So, how do we know that the rotation axis of the Earth is moving so much and with such accuracy? So it turns out that we have to rely on quasars. So the quasars are radial sources. And if you have a lot of radio telescopes pointing at the quasar, and you can correlate the signal coming from the quasars, you will have a very nice, I have a pointer. Doesn't work. Then you will have a nice correlation between the two, and then you can figure out what the motion of the planet is doing. So this is an animation that is taken from NASA that nicely illustrates what the rotation axis of the Earth is doing. So you have this precession that is with a period of about 26,000 years. That in geodesy it's called the secular motion of the axis. But on top of it, you have nutations, which is what I showed you earlier. This is in the XY direction, they look like that. And so we are concerned about these small nutations. So the thing is that we know the torques acting on the Earth. And we also know, as I showed, with very good accuracy how the Earth is moving, the rotation axis is moving. But what we don't know with certainty is what's happening in the interior, because that's what is actually, in other words, we know the forcing of the system, we know the response of the system, but we have not complete information about the system itself. So we have to use both the input and the output to figure out what's in the box. Okay, so you can make models of the Earth's interior, thinking of the mantle deformation, the loading of the oceans, the loading of the atmosphere, and have a very simple model of the core flow. And you can actually show that the signal from these notations can be mostly, for the most part, be explained. However, there is always a residual that is shown here for the X and Y component. Now, this is milli-arc seconds. At the beginning, I was showing you a scale that was about arc seconds. Now, this is in milli-arc seconds after you have taken into account deformation from atmospheric and ocean loading and that. But you see there is still a signal. That signal has information about the Earth's interior. And we want to find out what information is contained there. And well, from my point of view, the most obvious thing to do is to find a better model of the core flow, because what is done in geodesy usually is just to simply assume a uniform vorticity flow that is called the Poincaré flow, and they usually inviscid. And that's a very rudimentary model of the core flow. So we want to do better. So there are other things involved. For example, it could be that the core flow, in response of the Earth, can be influenced by the small-scale topography that could exist at the core mantle boundary. There might be a stably stratified layer that we don't know, still highly debated. We don't know either the lowermost part of the mantle, the conductivity of the lower parts of the mantle. And these are things that if you can put it into a better model, you may improve the notation models and extract information about all these features. But of course, this is a very complicated task. Oh, well, so this is just to show that there is seismic evidence for the core mantle boundary topography, at least at large scales. So you can think of this as maybe the undercontinent in the core mantle boundary. And you can even think of small mountains or valleys and things like that can exist in the core mantle boundary. I'll show you that maybe later that this could be important. So this is the main question that I'm trying to answer. Of course, it's going to be difficult to have a straightforward answer to this, but well, we're trying. So I'm going to start with some of the rotational models. Rotational modes of the Earth. So the Earth, as a solid body, has these 4 eigenmodes. They are called the free core notation, the free inner core notation, the Chandra wobble, and the inner Chandra wobble. The length scale is here. And there is also, on top of this change of the rotation of the direction, you also have the length of day variations that can give you information about, well, other kinds of information. The time scale is different, though. I'm not going to talk about this. I'm going to talk about only this one and this one in this talk. So there is I hope this, yes, it's this one. There is a little bit of confusion in the fluid dynamics community and the geodesy community because in the fluid dynamics community, we talk about sometimes of the tilt over mode. And we take it as a synonym for the spin over mode. And in geodesy, these two things are not the same. The tilt over mode has always frequency 1. It's exactly 1, always. The spin-over mode may have a frequency that is slightly different from 1. They have similar characteristics. The tilt-over mode, if you just imagine that the Earth is, imagine that the Earth is spinning, the rotation axis, and then you move the rotation axis, but in the rotation frame that you had before, then the frequency of the Earth will be exactly 1, anyways. So that's what this tilt-over mode is all about. It's actually like a trivial mode. It doesn't really have any dynamical relevance. What is important, or what is more relevant for us, is the spin-over mode and the free Corr notation. And these two are actually very tightly related, and I'll show you how. Well, there is a missing piece of the puzzle in the core flow. So it seems like there is some dissipation going on that is not accounted for, and we don't know from what that is coming from. So if you start analyzing the notation data and you make a model of the core flow as a uniform Poincaré flow, you can estimate these constants. This is the torques at the core mantle boundary, the torque at the inner core boundary, and you have these two constants, KCMB and KICB, that are proportional. Well, are the proportionality constants for the spin of the flow, the fluid outer core, and this one for the difference between the inner core and the outer core. So you see that the model is simply like the core flow, the outer core is simply it's like a solid body, but rotating. And these constants, if you estimate those constants from the notation data that I showed you, you have this value. And you can estimate what the viscosity, well, you need to have a model. You make a model of the core flow to compute these constants, and that depend on the viscosity and the magnetic field in the interior of the RMS magnetic field in the core. And you see that this line, for example, corresponds to no viscosity, and this line corresponds to a viscosity that is about 30 or 50 times more than what we think exists in the core flow. So you see that this value here is compatible only with a viscosity that is just too high. Although you can also say that, well, this line is actually the estimate of the magnetic field from the chaos 6 model that is based on observations, and that's extrapolated to the core flow, to the core mantle boundary. And it could be that the extrapolation is not correct, and in that case, this will be like the lower bound for the magnetic field, or it could be that I think is more likely the case that this is indeed the case, but there is another dissipation process going on, and I'll show you some ideas of what this might be. For example, Bruce Buffett in 2010 suggested that the internal shear layers, these are exactly the same ones that Michel Reutor showed you during the first talk, that there is possibly ohmic dissipation taking place in those internal shear layers. And even if you decrease the Ekman number, your viscous dissipation is going to decrease, obviously, but the ohmic dissipation is going to increase, as he is showing here. So he made a crude estimate, like sort of a back-of-envelope calculation that appeared in Nature, of what would be the required background magnetic field to account for the missing dissipation from the notation series. So he estimated an internal magnetic field that is about here. So we wanted to do a little bit better, because this is actually a very crude model. In this calculation, the back reaction of the flow, of the induced magnetic field to the flow is completely ignored. So we wanted to make, well, a real model. So we started, we kind of made a step backwards and started from the beginning. So we just have the simplest thing that we could imagine. We just imagine what is called a two-layer model planet, and we have a mantle that has some ellipticity. We include the ellipticity because if you don't have it, then the Chandra bubble doesn't exist. You have to have a different moment of inertia, the axis, the figure axis misaligned with the rotation axis, otherwise you don't have a wobble. So it wouldn't work for a sphere. And so we just started writing down the moments, the equations of motion for this, and we assumed that the rotation is very small. The misalignment between the rotation and the figure axis is very small, and we assumed a periodic motion. And I'm going to go a little bit into the details because they might be interesting for some of you. So then we start with the Navier-Stokes equation for the flow, for the interior part. And for the mantle, we are going to write down the torque equation, the angular momentum balance, by computing the torques exerted by the fluid on the mantle. So we're going to compute these two contributions. This one is the pressure torque, and this one is the viscous torque. So for the core, for the core, we start with a typical colloidal-toroidal decomposition, a spherical harmonic expansion of these two functions, and we're going to use a Chebyshev polynomial expansion for the radial direction, with one slight modification that might be of interest for you. That usually this is done using the Chebyshev collocation points that lead to dense block matrices. But we found a relatively recent method that uses instead Gegenbauer polynomials. And this actually leads to to sparse matrices for the Chebyshev polynomials and its derivatives, which is quite convenient because then your memory requirements are going to be very much reduced. Okay, so we write down then the Euler equations of motion for the rigid mantle that involve these quantities that are the torques exerted on it. And here, well, this is the torque we computed like this. And we have to establish some control parameters. And the control parameters that we're going to use is the flattening. I think it's over here. You can see what the flattening is. These are the difference between the major and major semi-axis. And also this control parameter that we call Q that says how thick is the mantle. So this controls more or less the moment of inertia of the mantle. Well, the inverse moment of inertia of the mantle. Okay, the actual equations that we are solving are these. They're a little bit slightly different, but just for convenience for the medical problem. And you end up formulating an eigenvalue, a generalized eigenvalue problem that we solve with standard tools. And one important thing is that we are using spherical harmonics, but we are using a spheroidal boundary. So we need to figure out how to write down the boundary condition very clearly, very carefully. So what we do is a Taylor expansion of the flow near the core mantle boundary, like this. So if this is the radius of the core mantle boundary, of the position of the core mantle boundary instead, and then you can estimate or build the velocity at the core mantle boundary, at the real core mantle boundary, using a third order Taylor expansion like this. But there is a small problem that you cannot really use too much flattening, because otherwise your Ekman boundary layer will be too far from the spherical region where you're starting to build your solution, and then you will completely lose accuracy. So we are going to restrict to very small flattenings that are relatively close to the, actually smaller than the Ekman boundary layer width. And then we set the shape of the core mantle boundary in a spherical harmonic suspension like this. Now, this technique of the Taylor expansion, we used it already for inviscid problems where you don't have this constraint. And it worked pretty well. We have a paper coming up soon that was written by Jeremy and one of his and us. And it works pretty well. But the difficult part of this method is that it's very tedious to do all these calculations. You know, you imagine this, that actually you have to, compute the powers of this expression, so you have a lot of products of spherical harmonics. It's quite horrible. But with a new tool that Anthony Trin, one of our colleagues, he wrote a Mathematica program, package, that does all this with relatively ease. Okay, so this is our system. It's actually quite simple. The control parameters are this: the Ekman number, the flattening, and the moment of inertia, well, the inverse moment of inertia of the mantle. Just to give you an idea of what this Q number might be for the Earth's mantle, for example, it takes this value. For Mercury, it's like this. For Enceladus icy shell, it has this value. Okay, some solutions for that. This is an overall view of the spectrum. And what I'm plotting here is the ratio of the kinetic energy of the mantle to the kinetic energy of the flow, the total kinetic energy of flow, but all seen from the steady or the average rotation rate frame. So that, because obviously in the mantle frame you have no kinetic energy of the mantle. So this is a spectrum of the inertial modes. Well, they are not exactly inertial modes because these are modes of the whole system, and they include the motion of the mantle as well. So you see that there is some ordering. I think this ordering is very much related to the ordering that Michel Rutor mentioned during the first talk. It's quite nice. And I also want to show you this mode and this other one. These ones correspond to the Chandra wall and to the free core notation. So it was nice to see this because with this model we recovered these two modes. And we wanted to see what was going on in the region, in the frequency region near the free core notation. So we started to do a sweep in the Q parameter. So Q equals 0 means that the mantle is undergoing just a uniform rotation. It cannot be, because the moment of inertia will be infinite. So it's just a uniform rotation. So if this is the frequency, this is Q. So these are the places where the spectrum reduces to the inertial mode spectrum, a purely inertial mode spectrum. And they match, well, we checked that they matched properly with the expected frequencies. But as you start increasing Q, the free core notation that is here, its frequency starts going up. Oh, let me show you, let me say first that this color is actually the scale damping of the mode. So it's simply the imaginary part of our eigenvalue. So this is colored in this way so that you can actually trace what mode is which. So here, this mode, for example, is this one. It's going down in the damping, but in frequency it's going up. And something very strange starts happening. There is what we think is an avoided crossing, because as soon as the frequency of the free coordination reaches, well, is somewhat close to one of these other modes, you see that the damping undergoes some crossings, but then it avoids this mode. And then it kind of, bifurcates and keeps going, and then like a whole dance of avoided crossings start taking place. So this mode avoids this one, but this one, by avoiding the other one, it bumps the other, and it keeps going. It's like some sort of a cascade, and we think that this can keep going, even lower in the damping. So this, how much minutes? Half a minute? Okay, so this is what happens in the complex plane. In the complex plane, this is the damping and the frequency, and these are the modes that do not have interaction, these ones. But this is the free coordination. This is the value Q. As you can see, when this one starts here, but ends up in another location that corresponded actually to the one that was earlier. So it kind of connects back. So you have a line connecting the modes. We actually have no idea what this is, but it seems like there is something there that might be of interest. And just to show you that this actually changes, but if you change the Ekman number, these avoided crossings can become, well, crossings or not avoided if the Ekman number is changed. So yeah, so I guess I'm running out of time completely because we all need some coffee. So let me just jump to the summary here. And say, well, we have discovered that the inertial modes can actually influence the motion of the mantle, and that these are good possibilities to start from this very simple model and make better notation models that could be useful in the future. And that's it. Thank you.
Okay, thank you for a nice talk. We have time for a couple of quick questions. We're sort of. Michel.
I was wondering, in the core of the Earth, the flatness due to centrifugal force or distortion by the tides is how does it scale compared to the thickness of the Ekman number when you have to compare the two, the epsilon of this perturbation? Because I would suspect that the Ekman layer is much smaller than the distortion of the CMB.
Oh yes. In the Earth, this is certainly much smaller because the Ekman layer, I think, has a scale of centimeters.
And therefore, one way to take care of that would be to do a mapping of the spheroidal geometry of the boundary to the spherical geometry, so that you are not
exactly.
constrained by this. We have done that for rotating stars, and so
well,
we can talk about that.
Yes, indeed.
Yeah, why not?
Have you looked at viscous dissipation with these modes?
Yes.
Can you say anything about that? Are there interesting trends that you've found?
Yes. So, well, the viscous dissipation, unsurprisingly, goes down with the Ekman, but let me see. Maybe this one is going to be a little bit of help. This is what happens when you decrease the Ekman number. But what we found out is that the viscous dissipation takes place mostly at the boundary, of course. And we have internal shear layers, I didn't show this, but we have internal shear layers coming from the eruptions at the critical layers. So these are not like the attractor, but these are actually eruptions from the internal shear layer, the Ekman boundary layer. And this interaction actually happens because of the dissipation in the boundary is probably increasing as you change the parameter Q. But also, there is another component that is the Poincaré force, because that produces work. So in the overall energy dissipation, when you compute the energy and compute how much, the damping factor of the total energy, one part is from the dissipation, of the viscous dissipation, but another component is from the Poincaré force. So that's what we found out. But we hope that ohmic dissipation is going to be much more important.
Okay, so I think we should thank Joel again. And just for that, we will recommence at 10:02. But thank Joel and all the other speakers this morning. Thank you.